Let's have a conclusion. What is hyperbolic geometry? It's the geometry of constant negative curvature, a geometry that provides more space than Euclidean geometry for a given dimension and has intrinsic hierarchical tree-like structures. Given these properties, the first success cases of hyperbolic deep learning was in embedding trees, graphs, and text, where just hyperbolic deep learning showed a great promise. Then, hyperbolic geometry was used in learning visual embeddings and in computer vision. Different methods are available in supervised or unsupervised tasks like image classification, zero-shot learning, action retrieval, or clustering, or just unsupervised object discovery.
Okay, thank you, Mina. So the real question is, maybe can you go back to this presenter mode? Then. If you want to shortly recap, why should you care about hyperbolic geometry? It's because both at the input and at the output level, hierarchies are everywhere. And I hope that in this morning we've shown that hierarchies and Euclidean space are perhaps not the best match, but that hyperbolic geometry is a better choice for this kind of data. And we've seen that already in these first cases, there are potential benefits for all of us. So we've seen better performance at certain tasks, and certain things keep on coming back. So we have very informative cues about uncertainty or ambiguity popping up. You see an example on the left here, and also in the segmentation example, where we've seen some very meaningful, let's say, instances of uncertainty naturally being part of hyperbolic geometry. We've also seen zero label generalization, so a few papers that did zero-shot learning explicitly or implicitly, and being able to generalize to new classes if you give the hierarchy as part of the training. And other cases include few-shot learning, etc., where we've seen just consistent improvements of Euclidean space over hyperbolic space. And as Jeffrey pointed out, also in the unsupervised domain, it's a very, let's say, almost a counterpoint, but in unsupervised domain, you can also have limited examples. And in that case, hyperbolic geometry is very prevalent as well. But it goes deeper. Did you know, for example, that if I have colors, well, we do colors in RGB, but if you really look at the wavelength, so you represent a pixel not by RGB, but as like the raw wavelengths, maybe bin it every 10 parts, that's hyperbolic. That's older literature on hyperbolic geometry. So certain color spaces behave more hyperbolic than Euclidean. This is things we've known from CFPR 15 years ago, but of course, in the deep learning era, we forget everything before 2012, but it's very much true. So these things I predict will come back. Did you also know that smell is hyperbolic? We don't do anything with smell, typically, because it's hard to get odometers for yourself, but smell behaves hyperbolic. There's even evidence that how V1 to V5 works in your brain is perhaps more hyperbolic than Euclidean. It lacks the empirical results for that. But there are a lot of cases, the deeper you dive into it, the more you see that things might not just be as Euclidean as you might expect. And if that's the case, why do we always have Euclidean networks? Should we not at least as an alternative have hyperbolic networks? And ideally, perhaps have both. So there's a lot of untapped potential. As you see, these are first indicators. So there are many papers to be written. Now, some question that coming back already a few times is, why do you only have the output space hyperbolic? Well, the practical answer is it's very hard to do the full network hyperbolic. So this is ongoing work. I expect that to be solved within half a year to a year. So really from the pixel level, do everything hyperbolic, and yeah, what is the benefit of that? Stability is another problem. So being able to do things very stable and without a lot of nonce was already hard for Euclidean domain. Well, after all these years, we've been able to get it a bit more stable. And the same needs to happen for hyperbolic deep learning. Another problem is that doing this forward-backward computations, as you've seen also from Martin's talk, just the basic operations become more complicated. So a Möbius addition is just more involved than a normal addition. So the computation graph becomes larger as well in deep networks. So being able to do the forward-backward passes of these things, make that more efficient is ongoing efforts. Curvature is a question that comes back a couple of times. Now curvature is a hyperparameter, but it seems to be very important. So very data dependent as well. Should we not learn the curvature? And ideally just have a network that's agnostic to the manifold and we just learn the curvature even if it's positive or 0 or negative, learn it on the fly. Last few things is that it mostly seems to be effective when dimensions are scarce, when examples are scarce, etc. But what about large-scale learning? Should we not just have stable diffusion with hyperbolic geometry? Should we not have huge vision transformers with hyperbolic geometry? And I think that's still completely not done yet, but that will be in the near future. And the same holds for multimodal learning. If we know that graphs and text and perhaps also vision are very suited for hyperbolic geometry, can we not just do them all together? And in that regard, there are many, many papers to be written. So let's say my positive 10-year outlook would be that in 10 years from now, this is all standard for us. We'll look back and about the weird times we did Euclidean geometry. And we just have, in PyTorch, you just have a manifold hyperparameter, and we set it, and we don't even think about it anymore. Yeah, that's my hope. More realistically, I hope and expect a more prominent role of hyperbolic geometry in both our community and in real-world applications, and especially when your metrics or data or labels are hierarchical. So if you want to avoid big mistakes, if you have these hierarchies, use them and then combine them with hyperbolic geometry. And hopefully, as much as possible, also with limited data and dimensionality. Ideally also with large scales, but that's of course a bigger problem. But perhaps 10 years from now we do another tutorial on Euclidean geometry because we've forgotten everything about it, because everything is hyperbolic. That I don't know yet, but let's see. For now, I thank you for your time and for all your questions. It was very good to see the interest also between the talks about people having hierarchical data or having done some work with hyperbolic geometry. So I want to thank Mina, who's here remotely, Martin, Jeffrey, and Serena for helping putting this all together and making all these slides, and also the notebooks online that you can use to play around with hyperbolic geometry and get familiar with it. That's it for us for now. Thank you all for your time, and if there are any questions, please let us know. Thank you.
And thanks, of course, also to Pascal for organizing this nice tutorial.
It's been mentioned that hyperbolic representations perform well on a small latent domain. And I have two questions on that matter. The first one is, how would they perform on large latent domain? And what is, like in size, what is considered small and what is considered large, respectively, latent domain?
So I will do the supervised part of that answer. So in the supervised domain, we've seen if you do it at ImageNet level scale, if we call that large, I think it's hard for hyperbolic geometry to compete. Let's say at the CFAR level or few shot learning level, it's way more competitive. So at few shot level, actually, consistently it's better. In zero shot also. Let's say in the tens of thousands of examples, it's very competitive. If you go towards a million examples, that's where hyperbolic geometry still has a lot to do. But that's for supervised. Maybe Jeffrey can say more about unsupervised in scale.
Yeah, I think in the unsupervised case, it's the question of dimension is most things work in small dimensions, and in higher dimensions, it tends to be mixed, and Euclidean methods tend to get better as the dimension increases, probably because, like the amount of space increases, like has been said in this tutorial. And was there a second part to your question that I didn't answer?
Yeah, sort of.
Sorry?
Yeah, my question has been answered.
Okay.
Thank you. Any other questions? Oh, we see some. Yeah.
Is there a trade-off between the dimensionality and the number of bits in a number? So hyperbolic network seems to have infinite precision at the boundary, right? So in that case, the number should be encoded in a large bit.
Yeah,
So
that's very true. So because a lot of things are at the boundary, so between 0.98 and 1, things for, let's say, floating point precisions, that's actually quite hard because they're small in terms of floating points, but large in terms of when you compute distances between them. So a lot of the stability also has to do with dealing with all these points close to the boundary where they get very small in terms of precision, the differences, but still meaningful in terms of hyperbolic geometry. So there are two directions. One is also what Mina showed is you can avoid being at the boundary, which is, I think, more of a hack. The other thing is there's work on mixed precision for hyperbolic geometry. So where dealing with these kind of issues will be a thing of the past, hopefully. So those are the two ways of dealing with it right now. But it's very much ongoing work, especially the mixed precision part is really recent. Thank you.
Yeah, so I have a question more regarding what Jeffrey was talking about in the last part. Why do you think that hyperbolic VAEs actually provide benefits? Because, like, to me personally, it's kind of strange, maybe for some particular domain, but why would I want to project points in a non-Euclidean space and regularize like a von Mises distribution when I can just apply like just do that with a normal distribution, you know? Like,
Yeah, it's a great question. I think the reason these hyperbolic VAEs are working is because they're tested mainly on hyperbolic or tree-like or hierarchical data. So it's not, I don't think they're making the claim that in all cases, this is the best way, but they usually test on things such as, you know, one of the major like toy examples is to embed like trees, for example, randomly generate trees and embed them. And these hyperbolic VAE works will test on this. And like simple examples like MNIST where, you know, there's maybe simple hierarchy, but for like large scale computer vision, I think it remains as open work to see where these hyperbolic VAEs will work and like in which cases these will work and you know how they will work and things like that. So I think it's very much an open research question. Yeah.
okay, thanks.
Thank you, great talks. Did you consider alternatives with similar assumptions, which like parallel alternatives to the hyperbolic space assumptions?
So can you repeat your question?
Yes. So the hyperbolic, when you present the data in the hyperbolic space, it's just this is one way to describe what's happened, but maybe there are other ways which are very different, but actually have the same underlying or similar underlying assumptions with similar consequences, similar results. And from the other direction, did you think of like maybe there is something like different underlying assumptions which can better represent the relationships, because hyperbolic is just one set of assumptions.
Thank you for clarification. So I think regardless of the manifold you choose, there are some implicit assumptions, even if you do Euclidean. So what I've seen, if you really look at the positive curvature for spherical, I think that's best suited when your data is really on the sphere or where the norm doesn't matter. So you only look at the angle. Then you really are very clearly in the spherical domain. I would say the difference between Euclidean and hyperbolic, we keep coming back to the hierarchical domain. I think that's either a hidden or explicit assumption that you might have. But I'm very curious to see if we let go of that assumption just in general. We just want to learn. Even if we do one-hot encoding of things, do we learn anything different? Because then we let go of this assumption, but there might still be benefits. I cannot answer yet, but hopefully in a future workshop or tutorial I can come back to that one. There's one more question.
Hi, I have two questions. The first one, is it possible to apply also to diffusion models? And the second question, does it make sense to do some analysis regarding the course of dimensionality with this respect?
So I think the first question about diffusion, right? So maybe Jeff, you can also say a few words. There are, let's say, I think for NeurIPS, in 2 months from now, if you go to NeurIPS, you will see Riemannian diffusion. But maybe you can say a bit more on the ongoing work in the unsupervised domain. So what I've known about it is it's ongoing, but you can see diffusion also coming back with also hyperbolic. But it's the same for VAE and GAN. It's first proof of concept, and it seems to work well, again, when there are constraints on the size of your data. But I would be very interested to see if you do diffusion at the level that has been done this year, what happens. But that's ongoing work. Those papers are a bit more theoretical in nature. But I would be very interested to see what happens if you do run it on those big machines they have at industry. So it's there, but very recent. What was your second question? The curse of dimensionality. Maybe Martin, you can also say a few words on the curse. Yeah, what we see so far is really the other direction, where compactness is really a thing. Where if your output space normally would be in the hundreds, they can now be in the tens. So I see some sort of logarithmic relation. So someone also in the break pointed out extreme classification. For example, in the textual domain, you talk about 1 million classes. Now there you get the curse dimensionality right back at you, because if you then do one-hot encoding, you need 1 million output dimensions. So I see a very strong potential for that kind of cases, where you can, let's say, undo certain limitations of dimensionality by just having this compact space. But that's more from a practical point of view. I'm not sure if you have more from Martin, from a theoretical point of view. No, okay. Okay, I'll repeat it. I think you're happy with my answer. Let's do maybe 1 or 2 more questions, and I think it's time for food. Right?
Yeah, so I think these self-supervised like triplet losses are usually done with the distance, so there's not like a direct relation to the angle, but as it turns out, like when you start to optimize these kinds of things, it turns out that if you naturally have the representations be far away, they will tend to, or like organize hierarchically, and then there, I guess, will be a corresponding difference in angle. Yeah, I think it's possible. It's probably possible to use the angle to also like do this kind of thing. But I don't know if I have seen personally any work that uses the angles directly. Yeah.
So I think it's time we wrap it up. So thank you all for your patience and for your interest in this topic. If you have any further questions, you want to read more, we will update the website with the slides and other things. If you want to know more, if you want to dive deeper into this, just contact us, and we're more than happy to talk more about this, also at the conference itself. And for now, I close this session. Thank you for your time.